Hey guys, so today we're going to be talking about the different types of waves and their properties. So what I want you to do, this is on page 5 of your packet. If you look at the whole page, it looks like this. So go to page 5 and we're going to fill in the answers. You can pause this video and fill in the answers and listen to the instructions. So we have two different types of waves. One looks like this if you had a slinky, and one looks like this. You'll notice a longitudinal wave, longitude lines go across. That's a wave that's going to move in the same direction as the energy is moving. Energy is moving left to right, the wave is moving left to right. So longitudinal waves, particles of the medium move parallel, that means in the same direction as the wave's direction of travel. Now if you look at transverse, I try to remember this by like a T, like this looks like a T. Energy is moving left to right, but the wave is moving up and down. And if you have something moving left to right and up and down, this would be a perpendicular line. So transverse waves, particles in the medium move perpendicular. So try to remember transverse, perpendicular, because a T looks like a perpendicular line. Okay, so what's the difference between these two types of waves? Be sure you get these in your notes. One, transverse, or my up and down waves like this, do not require a medium. That means they can travel through space. So if you think about what kind of waves travel through space, they're going to be like sunlight. Okay, so electromagnetic waves like light, visible light, radio waves that are traveled via satellite, X-rays, microwaves, infrared, gamma rays, UV. All of those are waves that can travel through space. So those would all be transverse. Also, if you've got up and down waves on a slinky, that would be transverse. Water waves that are going up and down, a stadium wave, like where people stand up and down and it goes side to side, or waves on a rope. So like if you're thinking about the battle ropes that people use sometime in the gym where the rope is going up and down, but the energy is traveling left and right. These do not require a medium. That means they can travel through space. So it's going to be important that you keep these two separate. Longitudinal, I drew it kind of like the slinky going left to right. These are sound waves. Pretty much all we will talk about as far as longitudinal waves are going to be waves like sound waves or earthquakes, seismic waves, waves that start at one point and go left to right. So sound waves do need a medium. Sound will not travel through space. You're going to need something for it to hold on to, like a solid, liquid, or gas. Air is a gas. That's why sound can be heard through air. Water is a medium that sound can be transmitted through, and so are solids. So if we flip over, the first thing we're going to talk about is the Doppler effect. So I want you to pause this really quick and write this in your notes. The Doppler effect is just what you hear when any kind of loud noise is passing you, like a siren or an ambulance. As the train approaches, the sound waves compress. That means they get really, really close together like this. And then the frequency is high, but the sound is loud. Okay, so if the sound is loud, the frequency is high, the waves compressed. But as the train or the car or the ambulance passes you, the sound waves spread out. That's called a rarefaction. So the frequency is going to be low. Sound is going to be softer. All right, so be sure you pause that and write that in your notes. So as the thing is coming closer to you, the frequency is higher. All right, so just like we did on the front page, we are going to compare electromagnetic waves to mechanical waves. All right. So electromagnetic waves are not going to require a medium. These are the ones that can travel through space. So automatically you think, what can travel through space? Well, light can. So light, radio waves, anything on that electromagnetic spectrum. Infrared light, gamma rays. The spectrum is in order of wavelength and frequency. That's important to know. So we can call these waves electromagnetic waves or transverse. They're both the same. All right, mechanical waves or longitudinal waves or compressional waves, we have lots of names for these, all are like sound. They do require a medium, which is a solid, liquid, or gas. They're going to be called compressional or longitudinal, and they cannot travel through space. So remember, these are like sound waves or earthquake waves. So what we're going to do in class is do a little demonstration about how sound travels, but we're going to talk about this. Think about particles in a solid. Particles in a solid are going to be the closest together, which means the sound particles can travel faster. In a liquid, they're a little bit more spread apart, so sound can travel a little bit slower. But then in a gas, even though you would think air would be the fastest travel for sound, because those particles are far apart, air is going to be our slowest method of transfer as far as sound goes. All right. Now you're going to turn to page 7. You'll look at the bottom of your page, and it's page 7. So the first thing I want you to do is I want you to pause this video and copy down everything I've written here for the electromagnetic spectrum. I have a way of remembering it, and it makes it really, really simple for me. And that is, rabbits mingle in very unusual exotic gardens. You'll find that's something that's easy to remember. Rabbits stands for radio waves. What you'll notice is here I can't even see one complete wave. That means the wavelength is very, very long. The frequency is very low. It's a very slow wave. As opposed to gamma over here, they're very, very close together. They have a very high frequency, very high energy, and a very short wavelength. So on the left side, we have low frequency, low energy, and long wavelengths. So that's usually pretty easy for me to remember. On the left, we have low, low, and long. Energy is very low. Energy increases as we go across. So frequency increases as we go across. And wavelength is going to get shorter as we go across. So on the right side, we have high frequency, high energy, and a short wavelength. So if I ask you which has a shorter wavelength, UV or infrared, you would say, okay, UV is farther to the right. It's got a shorter wavelength than infrared. Which one has less energy, microwaves or visible light? Well, microwaves do. So be sure you've got that. Now, the sun, we know our primary source of energy is going to be the sun. Now, we're talking about electromagnetic spectrum here. We're not talking about sound waves, just electromagnetic waves, all the waves that are on that spectrum. The sun loses energy by emitting light, so most of its energy is left as light and heat. So this is a transfer of energy from the sun to the earth. Only a tiny fraction of light is going to actually reach the earth. So now what I want you to do is flip over to page 8, and I'm going to zoom out a little bit, and you're going to pause it and copy down these answers, okay? Copy this down. I think you've got it all the way there. Yeah. All right, so I'm going to focus that a minute. Y'all copy that down, and we're going to go through it in the notes. Okay? So, if we look at this, the sun's energy arrives as light. Okay? And it consists of visible light, infrared, and ultraviolet. All right, so visible light is what we can actually see. You'll see it's right here in the middle of the spectrum. It has all of the colors that we can see with our eyes. You'll notice the wavelength is kind of in the middle. It's not too short, so we can't see it, but it's also not so long that we can't see it. Visible light, you'll see that in rainbows a lot of times, and you can see the colors are also in order on that spectrum. And you've probably heard of Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. You'll notice that Roy G. Biv, if you were to write that on your spectrum, would start from the left and go to the right. So when we look at Roy G. Biv, you'll notice red is on the left. It has a longer wavelength. Violet is on the right, and just like our spectrum, it's going to have a higher energy, higher frequency, shorter wavelength. Okay, so visible light, as we see here, we start, now this is backwards, so you kind of have to be careful the way you look at these. Sometimes they can go from left to right, sometimes they go right to left. So sunlight is not just one color, it's actually what we call white light. It's made up of all of the different colors mixed together. So when light from the sun is refracted or bent, remember this is not rarefaction, this is refracting, bending of light, we end up seeing the colors. Just like this, when sunlight comes in, if it bends, sometimes we're able to see the colors because that bending slows down the light so that we can see it. All right, so infrared light, this is your second little paragraph with a little arrow in your notes, has longer wavelengths and carries less energy than visible light waves. So all of your warm bodies are going to emit infrared light. So they use this in the military a lot of times. But notice right here, really quick, visible light, you'll notice it's arranged just like the spectrum. So your blue colors are going to have a lot higher energy, higher frequency, shorter wavelength than your red. So infrared light, you've seen this a lot, I'm sure. The hotter areas are red, the colder areas are blue. And they use that a lot of times in night vision things. Also, they can use it in space and in weather patterns. All right, so infrared is going to be like when you use a remote control. Infrared waves are what connect the remote to your receiver. And that's based on how the wavelengths sit on the electromagnetic spectrum. They're exactly the same as your wave speed of your body heat. All right. Now, ultraviolet light. This is your next little arrow. These are wavelengths that are shorter than those of visible light. So ultraviolet over here, the wavelengths are shorter than visible light. They're closer together. And they carry more energy. They're farther to the right. They carry more energy, higher frequency than visible light. Ultraviolet is what causes sunburn. This guy sat in a truck with this side of his face facing the the window, and so that's what caused him to have all of this damage to his skin. So ultraviolet comes from the sun, and we do have our skin to protect us. We also have the ozone layer to protect us from ultraviolet light. All right, so we see the ultraviolet light. Some insects can see it. We can't see it with our own eyes. And it's used in tanning beds, okay? And you can see that radiation from the sun is not something we want to absorb with our skin, which is why we try to protect ourselves sometimes, okay? So if we look at this, we have different types of things that happen when we have light shine. Sometimes light shines straight through, that's transparent. Sometimes you can sort of see like a cloudy window, and then opaque would mean that's translucent. Opaque is when you can't see through at all. So opaque is when no light can pass through. And then like you see here, no light is passing through. Light can bend around it, but it can't pass through. Translucent is like if you held up something plastic or a leaf or something you can sort of see light through, but not images. So translucent is like a stained glass window. But if it's transparent, light can easily pass through and you're able to see through it perfectly. All right, so one way to remember, transparent, your parents see everything, and opaque, some light can pass through, and translucent, some light can pass through, and opaque, nothing can pass through. All right, so what I want you to do now is you are going to look at page 9 and 10. First, I want you to look at page 9, okay? So everybody look at page 9 in your packet. I'm going to pause this here so that you can have the answers, but I do want you to try to answer these with your electromagnetic spectrum. All right, so I'm going to zoom in just a little bit to where you can see all of it. Go ahead and pause it and get your answers. And then pause it here and get your answers. All right, and that is it for today.